Welcome back to another exciting episode of Dave Does Math from Home. This is part 2 of our video series on section 6.3, which is volumes of rotation. Still says volumes of rotation 1. It says that because there are two separate sections of this book that are both dedicated to volumes of rotation. There are two major techniques we're going to use. This section is only about the first of those techniques. So we'll talk more about the other technique when we get into section 6.4. But we're still in 6.3, and this is part 2 of the video section for 6.3. So we're going to work real hard to try and keep those things separate. In the first part of the 6.3 video, we talked about some of the theory behind how to do volumes of rotation, and we did one example very thoroughly about bullet bill. And so in this video, we're going to do a couple more examples, see if we can get a hang of what's really going on here. So the next example I want to talk about is, we're going to look at the function y equals 1 over x, which looks like this. I'm going to look at the interval from 1 to 4 on this. So here's x equals 1, here's x equals 4. This is the area that I'm going to be spinning around the x-axis. Well, yeah, let's do rotating around the x-axis first. That's what we want to start with, spinning around the x-axis. So when we spin this thing around the x-axis, we're going to get a shape that kind of, we'll basically take this shape and we'll spin it around down here, and you'll get something that kind of looks like this. My marker's dying. Hopefully that's showing up on the video. It looks like it kind of is. Turn up the contrast on your TV. So you get a shape that looks like this, and it's kind of, the 3D version of this, you can kind of think of this as like, it's like the bell of a trumpet, or pick your favorite brass instrument, like a trombone or whatever. This kind of flares at the end like the bell of a trombone. So we're going to find the volume of this horn, trumpet, trombone looking thing. And we're going to do it, as always, first we have a picture, that's step 1. We're going to slice this into very small strips of rectangle. This is my rectangle. When you slice this anywhere along this, you get a rectangle that goes from the x-axis up to this function. And when you spin this rectangle around the x-axis, you're going to get a disk, a thin vertical disk. And so the volume of our disk is pi r squared h. I will strongly encourage you to just always write this as part of your solution process, just so that, I know it feels awkward writing the same thing over and over and over again, but I genuinely think this is helpful. I always write this every single time. It's going to be tempting to try and like skip right to the integral, but I would encourage you to not do that. Take it step by step. Take it slow. There's no reason to rush this. So we know we have a disk. We know it has this volume. We need a radius. The radius of this disk is going to be from the center to the edge, which is a y value, which is 1 over x. And the height of this disk is going to be the thickness of the disk. That's dx. So we have our radius, we have our height. That means we know the volume of the disk is pi times 1 over x squared times h. Or not h. You know what h is. It's dx. So that's our volume of one disk. To get the volume of the entire shape, because each of these disks is going to have a different size, different radius. So to get the volume of the entire shape, we're going to have to add all these infinitely many tiny disks together. So the volume of our trumpet thing is going to be, so pi is still a coefficient. Coefficients are still safe. That can stay on the outside of the integral. We will have the integral. This simplifies into, I'm going to 1 over x squared simplifies into x to the negative 2. So that's how I'll write that. Dx. And I still need bounds on the integral. I'm not asking for an antiderivative here. I'm asking for a volume. So I'm going to have to go from 1 to 4. That's the hard part done. The hard part is setting up this integral. Now that it's set up, well, we just have to evaluate it, and that goes pretty straightforward. Pi hangs out on the outside. The integral of x to the negative 2 is negative x to the negative 1. And we're going from 1 to 4, which is pi times negative 1/4 minus negative 1, which is positive 1, 3, minus 1/4 is 3/4. So this volume is 3 pi over 4. So that's all pretty straightforward with the evaluation. It's the setup that's often the challenge here. This part is where I see students make the most mistakes, trying to figure out what shape you get, how you should cut it, what the radius is, all that sort of stuff. This is how you do it. We're going to slide into another example. It's going to start looking the same, and then it's going to get weird in kind of a hurry. So stay tuned. I'm going to use the same function on the same interval. This function still looks like this on that interval. I can do a better job of drawing it than that. That's a little better. I'll take that one. Okay, so we're still on the same interval from x equals 1 to x equals 4. This is still the area I'm interested in. Only this time, I'm not going to spin it around the x-axis. I've already done that. I know the answer to that one. This time I'm going to spin it around the y-axis, and we're going to see what it looks like this way. So the big difference this is going to make for us is that if we want to get disks out of something spinning around the y-axis, we can't do these vertical slices anymore. If we do vertical slices, if we cut this up into little vertical rectangles like we did in the last problem, they're not going to be disks. They're going to be some other shape. They're going to be like a shell, like an empty cylinder. That's not going to help us, not right now. If we want disks, we have to cut this thing horizontally. Which, if we're being honest, is not really going to give us disks. When we spin this shape around the axis, we're going to have a rectangle here, a rectangle here. We're going to get not quite a disk. Spinning this around the axis is going to give us a disk with a hole in the middle, because this rectangle doesn't touch the axis of rotation. If it touched the axis, then we would just have a solid disk like normal. We can proceed normally. This is going to give us more of like a donut shape, or like I guess I've been comparing this shape to like a CD or a DVD. This is kind of actually the much better example of a CD or a DVD shape, because it has that little hole in the center. So it's only going to be most of a disk. You could think of it as some sort of donut-like. Donuts are my favorite word to describe the shape of this thing because I really like thinking about donuts. So I'm going to call this thing a donut. And if we want the volume of this donut shape that happens when we take this thing and rotate it around the axis, then we need to figure out, generally speaking, what the volume of a standard issue donut is. And in this case, we're going to have the volume of the big disk, which is pi r2 squared h. I'm going to call it r big. This would be the volume of the entire disk if the disk was solid. But because there's a little hole punched in the middle, we have to subtract the volume of that hole. And that hole is its own little like absence of a disk here. So we're subtracting out the small empty cylinder, empty disk part from the big disk that's the whole solid thing, and that's how we get our donut shape. So we need to figure out what all of these things are. Pi is going to be, or I don't have to tell you what pi is, you know what pi is. R big is going to be, for the most part, R big will be the function up until about here. At this particular y value, something weird is going to happen. But for most of this, the radius of the big cylinder will be an x value, and that x value, we're going to have to flip this function around to get it. So if y equals 1 over x, then you can flip everything upside down, and x equals 1 over y. So this x value is 1 over y. That's the big radius. H, in this case, is going to be the height of this little disk. And that's dy for us here. Usually it's a dx when we put it on the x-axis because it's a tiny, tiny little chunk of the x-axis. But if we're going to cut this thing horizontally, then it's going to be dy. And r small is nice. The radius of the small cylinder that we're sort of punching out of the middle of this is just always 1. So that's convenient. Now we have to talk about the bounds on this. Oh, I guess we could talk about that in a second. The volume of our total donut is going to be pi times 1 over y squared dy minus pi times 1 squared dy. This looks kind of like a mess, but this simplifies really nicely. We can say that this is, we can factor out the pi in front. We can say that the rest of the volume is 1 minus y squared, or 1 over y squared minus 1. And we can factor out the dy on the back end. So this is going to be the volume of our donut. We can find the volume of our shape. I guess I should talk about the shape a little bit. When we spun this around the x-axis, we got like a trumpet bell kind of shape. When we spin this around the y-axis, we're going to get a shape that's much more like a paper mache volcano you see at the junior high school science fair. Like there's a cylinder, there's a hollow cylinder right through the middle, and then it's a round thing that sort of slopes downward on all sides. Looks like a volcano, including a hole in the middle. So the volume of our volcano is pi is a coefficient that can stay on the outside times the integral of, I'll worry about bounds in a second. I'm going to call this y to the negative 2 minus 1 dy. So right now we are set up to successfully complete an antiderivative, but until we put some bounds on this thing, it's not going to help us. We can't use 1 and 4 because those are x values. And hopefully at this point you have realized that we are not integrating on x. We are integrating on y. So we need these bounds to be y values. We need the top y value is here. It's this thing. All I know about this point is that it's on this curve, y equals 1 over x, and that x equals 1. So I can use that. I can plug x equals 1 into this to find my y value, which I think should also be 1. And that's the top y value. The bottom y value is going to be a bit of a mess because I'm not following this curve outward all the way to infinity. I'm only following this curve out to x equals 4. At this point, I'm going to stop following this, and if I put another rectangle in here, this rectangle isn't going to chase that function outward. It's going to stop at x equals 4. So this is the point where I'm going to end on the y-axis. And that's going to be, when I plug in x equals 4 into this, I'm going to get y equals 1/4. So y is going to go from 1/4 to 1. This will give me the volume only of the top half of this. I'm going to have to do something else to deal with this bottom chunk right here, but the nice thing about this bottom chunk is that it uses both the right and the left edge are constants. This is x equals 1, this is x equals 4. There's no real variation there. We could find the volume of this bottom chunk just using geometry. We don't need to use calculus for that. We have to use calculus for this piece because the radius is changing. It's constantly growing. So we need to use an integral to collect all those different y values between 1 and 1/4 and integrate across all of them. But on this bottom piece, we're safe. So I'm going to finish this integral. Pi is a coefficient that can hang out. The integral of y to the negative 2 is negative y to the negative 1. The integral of negative 1 is negative y. And I'm going from 1/4 to 1. I'm going to start moving in this direction for space. I'll have a pi. I will have negative 1 over 1 minus 1. That's what happens when I plug in 1. Minus pi times 1/4 to the negative 1 is 4. So that'll be a negative 4 minus 1/4. This first part's pretty easy. 1 minus 1 is 0. The second part, I'm going to keep moving backwards. So this is negative, well, let me do this. This is 4 and 1/4. Pi. I guess I should change that into a improper fraction. It'll be negative 17/4, but then it's negative again, so positive 17 pi over 4 is the volume of the top half. Still missing this bottom little rectangle here that doesn't change. We can find this bottom little rectangle using geometry, since we know the height will be 1/4, and we know the width will be, our big is 4 and our small is 1. So we can find that using just the standard donut formula without using any calculus, or you could get the calculus involved if you want. It will give you the same answer. I'm just going to use geometry. times 4 squared, the height here is 1/4, minus pi times 1 squared times 1/4. This has turned into quite a mess, and I apologize for that. This will be 4 pi minus 1/4 pi. So 15/4 pi. So this is the area of, or the volume of the bottom piece. So altogether, the volume of this entire shape is 15 plus 17 is 32. 32/4 is 8 pi. Whew, that was a mess. And we're at 21 minutes. I'm surprised the video hasn't cut itself yet. I'm going to cut it pretty much immediately. I just want to say before I do, this is a horrifying mess, but it's a great example of why we need two separate techniques to do these volumes of rotation. The technique we are going to learn in section 6.4 to do a problem like this is going to be effortless by comparison. You're going to love it, trust me. Expect a part 3 of this section coming so that I can do more examples that aren't abjectly horrifying and 20 minutes long. Bye.